I would like to talk at first about a bit about the development of the theory of metaphor. And in fact, the theory of metaphor has gone through 3 stages. And since in general scientific theories are metaphorical, and I will talk a bit about that, I'd like to talk about the metaphors for metaphor that the theory has gone through. At the very beginning, I've mentioned in previous talks and in Metaphors We Live By, a metaphor called love as a journey, in which lovers are understood as travelers and relationships as vehicles and difficulties in the relationships as impediments, things that get in the way of traveling to a destination. And those are the linguistic expressions for this conceptual metaphor are things like it's a long bumpy road, we're spinning our wheels, we're going in different directions, and so on. But in each case, there is a mapping from the domain of travel to the domain of love. Now, that mapping is the following, that travelers map onto lovers, vehicles to love relationships, that the destinations, common destinations, map onto common life goals, and that impediments to travel, things that stop you from reaching your goals, map onto difficulties in the relationship. Now, originally, we tried to use the metaphor of the mathematical mapping for this, and it failed. It failed for an interesting reason. In a mathematical mapping, where you are mapping from one structure to another structure, perhaps one set to another set. Let me give you an example of a mathematical mapping. You multiply by 2. You take 1 maps onto 2, 2 maps onto 4, 3 maps onto 6, and so on. Okay? Mathematical mapping. In each case, the source and target of the mapping exist independent of the mapping. Right? The mapping cannot create new structure, and it just all the structure is there, and you just map from one pre-given structure to another. Nothing is created. Okay? Not only that, nothing is overwritten. I mean, you map everything there is to be mapped. So it turns out that this failed for a couple of reasons. The first reason is that real conceptual metaphors can add structure and add entities. For example, in the domain of love just by itself, where you have an emotion, a lover, and a beloved, and some positive emotion, there is no such thing just in love by itself as a crossroads, as a direction, as a dead end, and so on. All of those entities are added by the metaphor of love as a journey. That is, love as a journey adds entity structure to a love relationship. It introduces new entities. And that is something a mathematical mapping cannot do. So that was one failure. A second failure was the following. There are cases where certain things are not mapped. And in general, they work like this. I gave one of these examples before. Take the sentence, I gave you that idea. In I gave you that idea, if I say I gave you this bottle, then I no longer have the bottle. But if I gave you, if I gave you the idea, then I still have the idea. What's going on? What is happening is this, that you know something different about ideas, and the metaphor overrides what you know about that idea. So, in order to account for the first problem, the addition of structure to this, we made up a new metaphor for metaphor. It was the the overhead projector metaphor. You know, where you put layers of projections on and you project them on an overhead projector? Well, you can add structure that way. And so we have an overhead projector metaphor. I think we have some room on the floor down here. So if that's possible, you know, please come in. Now, so one additional metaphor is that you can add entities that way, but it's a funny metaphor. It's not a real theory. It's just a way to think about it. But in the case of I gave you the idea, you are subtracting structure, and adding overhead doesn't allow you to take account of that. Now, what we did was simply stipulate that when there was a contradiction, you had what was called an override. Now, that was an ugly theory. In fact, it wasn't even a theory. It was a way to name the problems. More recently, in Narayanan's neural theory of metaphor, you have an explanation and a real theory of these phenomena. The neural theory says that certain basic primary metaphors are learned very early, and they're learned under conditions of experience. For example, you learn that achieving a purpose is reaching a destination. Because why? If you want to go and get a drink of water, you have to go to where the water is. If you want to get a book, you have to go to the library to get the book. That is, achieving a purpose regularly correlates with reaching a destination, and that correlation activates different parts of the brain. When you activate different parts of the brain, you learn regularly, over and over, you learn neural connections between them, and those neural connections physically constitute the metaphor, the primary metaphor. Now, what that says is, first, if there's a contradiction between the two domains, if any parts are inconsistent, then the connections are never made. And so, I gave you that idea, there would be no connections to override. They would just never occur. Moreover, you could explain on this account why structure is added. And the reason is that metaphorical reasoning would be taking place in the source domain, with the effects of the metaphorical reasoning mapped over. That is, if you are reasoning, let's say, about purposes in terms of motion through space to a destination, then your reasoning is about motion through space, and the results of that are mapped over to what you say about purposes. So in that account, you have an account of why extra entities, the entities of the source domain, are used in the target domain when you are thinking metaphorically. So this is a nice example of the history of science. We went through 3 stages, each with a different metaphor for metaphor. And the last metaphor for metaphor, namely the neural connection metaphor, is a real scientific metaphor. It's something that can really occur in biology, and it makes a lot of sense. But it's important, again, to understand that if you're talking about something scientific and abstract, you're very often using metaphors. Let me give you some more examples. Let's take Einstein's theory of general relativity. I assume that at the MIT of China, I'm allowed to talk about scientific issues. Einstein used one of the most common everyday metaphors in the theory of relativity, namely that time is a dimension of space. And we have this metaphor universally. We have 2 metaphors for time, one in which time can move toward us and one in which we can move along the time dimension in space. And both occur in languages around the world. Einstein took that second metaphor and took it as a truth of time, a truth about physics. Now, in general relativity, Einstein took up the question of what is gravity. And he argued the following. He argued that there was no such thing as the force of gravity. That gravity, as a force acting at a distance, did not exist. That Newton was wrong. What he said instead is that gravity is a curvature of space-time. So let me give you an example of this. He said, think about a star, or the sun, okay? And imagine during, a light from a distant star passing by the sun. The question is, does it curve? Well, light, a photon, has no mass. If it has no mass, it can't be pulled to the star by attraction of a mass, as in Newton. Then it should go straight. But, he said, there's another way to think about the behavior of, say, objects with masses going by a large object like the sun. Imagine, he said, a rubber sheet, like a rubber sheet, a flat rubber sheet. You put a basketball on the rubber sheet and it goes down. It curves. You take a marble, a little marble, and you shoot it right past the basketball and it will curve. Not because there's gravity pulling it to the basketball, but because the rubber sheet, the space, is itself curved. And he said that a photon going by the sun should curve. This was experimentally tested in 1919 when there was an eclipse of the sun. And during the eclipse, there was a star right behind us, right next to where the eclipse was. And the question is, where would you see the star? Would the light of the star be over, would the star look there with the light coming straight? Or would the star be there with the light curving so that it would look there, but we know it was over here? Or would it just come like this? And the answer was the light curved. The star looked like it was in a different place, right? The light curved. What that meant was that it couldn't be pulled to the sun by gravity, so space itself had to be curved around large bodies. Now, that was the Einstein's account. It's a wild metaphor. What he's doing there is using a certain form of mathematics, Riemannian geometry, in which spaces can curve. For example, take a sphere. The surface of a sphere is curved. It's very common to have spaces that curve. Or take a saddle on a horse. The saddle, as a space, is curved. It's a plane, but it's a curved plane. So there are plenty of curved spaces that we experience in the world. And Einstein said four-dimensional space-time is itself curved in certain ways. And it's curved when there are large masses near it. Now, this is a very strange idea. It says there's no force of gravity. None at all. No force of gravity. Gravity is just curvature in space-time, always. So that when you fall on the ground and you hurt yourself, no force, just curvature in space-time. But falling hurts. Curvature shouldn't hurt. That is, what Einstein did was introduce a very, very beautiful metaphor into physics that allowed him to do all the computations correctly using a single mathematics, Riemannian geometry. But it's strange because it postulates that there are no forces. It says a metaphor that says force is curvature. There's another way to understand it, which is that curvature in space-time is a very good metaphor for computing for what will happen when you have gravity. That's a very, very different understanding of Einstein. There's one understanding that says what Einstein said is literally true. The metaphor is true. There's another understanding that says the metaphor is an excellent way to understand the world and do computations about it. But it's still a metaphor, and there still is a force of gravity. Okay? Two different understandings. I prefer the second. Okay? Now, what's particularly interesting about contemporary physics is that there are multiple understandings for concepts in physics. Right now, the most popular concept is, one of them is string theory, in which you have the universe as, I believe it's now a 10-dimensional space, where there are 4 normal dimensions, 3 plus space plus time, and then 6 other really small dimensions, and there another metaphor is used. And it's a kind of interesting metaphor. If you think about the study of elementary particles and forces, let's take elementary particles. In quantum mechanics, traditional quantum mechanics, before string theory, had a metaphor that each particle is made up of smaller particles called quarks, and when particles interact, they give off other particles and absorb other particles. They exchange particles, and the particles carry properties like spin and charge and mass. Okay? And that the changes have to do with what quarks are exchanged in these interactions, and therefore what properties are exchanged. This theory is based on a very common metaphor that we all have, that properties are objects that we possess. We can say, I have a headache. My headache went away. I got a headache. The noise gave me a headache. The aspirin took my headache away. You can understand the headache as an object that comes to you, as this object that you have, a property. And in classical quantum mechanics, that's how elementary particles were understood. Their properties, like mass and charge and spin, their properties were understood as objects that they possessed. Now, there's another way for objects. Notice we can say, I have a headache. You can also say things like, I have trouble. I have troubles. My troubles went away. Okay? That took my troubles away. The music took my troubles away. There are two ways to talk about trouble, either as an object you can possess or a space you can be in. So you can say, I'm in trouble. He got me out of trouble. He got me into trouble. Okay? As it can be understood also as a region of space. So that a property that something has, namely me being troubled, can either be seen as a possession, an object I possess, or a region of space that I'm in. What superstring theory does is change metaphors. It says that instead of the object metaphor for properties like spin and mass and charge, what we'll say instead is that there is another spatial dimension for each of those, and that the particle is located along that spatial dimension. Okay? So it's located, and the spaces are very small. So for example, for charge, there are only 3 locations, plus, minus, and 0. For spin, there are 5 locations, plus 1, plus a half, plus a 0, minus a half, minus 1. And they're very, very small in terms of numbers compared to other numbers. So these are small dimensions, and the idea is that some dimensions are long and some are small, and if you think of an image of something like that, it's like a string, which is long in one dimension and small in other dimensions. Right? Hence, string theory. Okay? And therefore, each particle can be thought of as having having a location in a 10-dimensional space. Right? That is, it's a metaphor shift to go to that. And why would they make the shift? Because you can then use Riemannian geometry again. Riemannian geometry is the geometry of multidimensional space, which can be curved. And since it can be curved, you can you can again say that gravity is curvature, but now you can say that every force is curvature and generalize. And now all force becomes curvature, and then everything in the universe is just geometry. Now, if you take string theory literally, everything in the universe, including you're just geometry. You're just made up of a lot of points in space. All right? You don't exist as you. You're just a lot of points in space, and that's very strange. I think it's impossible to make sense of that theory of physics literally. I think it makes perfectly good sense metaphorically. It says, this is a really good way to think of physics if you're going to do computations linking space and time and charge and spin and all of these different ideas in one mathematical system. This is a very useful metaphor to use, but there's still force there, and there's still you, and you're you, not just geometry. So what I'm suggesting is that all science, especially physics, is metaphorical, and that it's necessarily metaphorical. And if you look at the magazine Scientific American last August, it's a wonderful article in it for those of you who are interested in physics at all. It's an article about a different metaphor for physics altogether, the information theory metaphor for physics. It's an article it's a theory that starts with thermodynamics, which is based on information and information theory, and then it says, let's keep that idea, and instead of moving to string theory, consider everything as information. Everything in the universe as information. And then they extend the metaphor more and more so that now there is a complete theory of physics in terms of information. No geometry, just information. What you have are two utterly different types of metaphors for the physical universe, and it turns out they're equivalent. All the predictions made by one can be made by the other. You can map one theory into the other theory. That is, these are two different metaphors, two different ways of understanding the world in terms of one kind of mathematics or another kind of mathematics. But it's strange to take either of them literally, because you are more than information. You are you. Force is force. And so on. It just says the information theory metaphor is a useful metaphor. Now, this is a revolutionary way of understanding what science is, and I think it's a correct way and an important way. And what's particularly interesting is that the same is true of mathematics itself. I have a book written 4 years ago, with Rafael Nunez called Where Mathematics Comes From. It's a nice big 600-page book. I like 600-page books. And the reason I like 600-page books is that only then can you really get into all the details. What we did was not just take simple mathematics. We started with addition and multiplication, but we went up to very, very complex higher mathematics. The last chapter of the book is about 80 pages long on the formula e to the pi I plus 1 equals 0, and it explains what it means. I won't do that today, but I will explain to you why that is an appropriate problem for metaphor, for the theory of metaphor. Think for a minute about that formula. E to the power pi I plus 1 equals 0. Or because it has the 5 most important numbers in mathematics, e, pi, I, 1, and 0. Very interesting formula. Now, think for a minute about raising something to a power. When I was in high school, they told me that raising something to a power was multiplying it by itself a certain number of times. So 2 to the 5th power is 2 times 2 times 2 times 2 5 times. That is 32. Okay? So raising something to a power is multiplying it by itself. This cannot be true for this formula. Why? First, what are you raising? You're raising the number e. E is an infinite decimal. 2.1828, 1828, dot, 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 dot. Okay? Goes on and on and on, infinitely. Okay? Now, how do you multiply? Multiplication is given by an algorithm, and you start on the right. This is infinite. Where do you start on the right? There's no right. It goes on and on and on, infinitely. There's no place to start. Problem 1. Problem 2, what does it mean to multiply a number by itself a pi number of times? 3.14159 dot, 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 as it goes on infinitely. That is not a number of times. It doesn't make sense. And finally, what does it mean to multiply a number by itself an I, that is the square root of -1, number of times, an imaginary number of times? Makes no sense. You can't think of doing it. That is, what that means is that raising something to a power cannot be just multiplying something by itself a number of times. It must be something else. And in the process of doing this, we discovered that something else was a very interesting metaphor. And it's described in the book. If you want, we could go into it later. But it turns out that in order to describe and understand what that formula means, it has a meaning. To understand that it has a meaning, what it means, why it means it, requires about 15 different metaphors from 5 branches of mathematics. And what we did in the book was work out all those metaphors in all those branches of mathematics and then show how they get put together in this formula. Now, that's an advertisement for the book. Let me try to give you an example from it that's kind of interesting. Have you ever wondered what infinity is? Anybody think about infinity? Well, there are 2 kinds of infinity, so you might be thinking about 2 different things. The first kind of infinity is called potential infinity. Potential. Why? In potential infinity, for example, you start to count. You go 1, 2, 3, 4, and you go on, and you never stop. That is, you never reach any infinity. It's just potential. Similarly, in geometry, what would potential infinity be? You take a line segment and you double it. You make it twice as long. And then you double that, and you double that. And you keep making each line segment twice as long, over and over again, and you never stop. It goes on and on, and that is potential infinity. By the way, there still are some seats down here if some people are stuck in back. Now, there's another kind of infinity called actual infinity. Actual infinity is very different. In actual infinity, for example, you may have the numbers 1, 2, 3, 4, 4, 5, the integers. They may go on and on forever, but there is a single set that contains all of them. That's the set of natural numbers. It's the smallest set that contains every one of them, an infinite number that never stops. But it never stops. How could it get all of them? Right? Strange idea. That's what actual infinity is. Let me give you another example. There's a form of geometry called projective geometry in which when you make line segments longer and longer and longer, they go on and on, but eventually they reach a point at infinity. They never stop, yet there is a point at infinity. And not only that, all parallel lines meet at infinity. Okay, this is a job for metaphor. right? That notion of actual infinity has got to be understood somehow. What is the mechanism for understanding it? Not only that, there's a further question. I just gave you two examples of actual infinity. One of them was a set of an infinite set. Another one was a point at infinity. Are there other such examples? The answer is yes, there are many of them. There are many forms of actual infinity in mathematics. And for example, take mathematical induction. You've probably all seen mathematical induction. It means if you prove that something is true for 0, and you prove that if it's true for any number n, then it's also true for n plus 1, then if it's true for 0, it's true for 1. If it's true for 1, it's true for 2. If it's true for 2, it's true for 3, on and on and on. But then it has to be true for all the natural numbers, even though you never reach an end. What does that mean? That's actual infinity. And similarly, there are transcendental numbers. Cantor's Aleph null is the number, the size of a set that has actual infinity. And then there are degrees of other infinities requiring other metaphors. All right, what we discovered was something interesting. That there, in fact, actual infinity is metaphorical. After all, think about it. If you never have encountered infinity, how can you understand it? The answer is by metaphor, in terms of ordinary processes. But what ordinary, everyday, finite processes allow you to understand actual infinity? Right? Not only that, we discovered that there was a single general metaphor for every form of actual infinity, with each type being a special case. So let me try to tell you in about 3 minutes what actual infinity is, once you understand what the theory of metaphor is. The way to think about this is in terms of the linguistic concept of aspect. We've talked about aspect before. Aspect is the structure of event. And there are various kinds of aspect. There's an initial aspect, what is called an encodative aspect, which is the first part of an event when you're first starting out. There's another aspect which is continuative, when you do something continuously. There's one that is when you do something instantaneously, instantaneous aspect. There's one where you repeat things over and over called iterative aspect. There's one where you finish something called perfective aspect. You have finished it, made it perfect. And one where you go on and on, but you don't finish it. So, a word like walk. Walk does not have any particular endpoint, so it's imperfective. If I say walk 10 steps, that's perfective. It has an endpoint. Now, potential infinity is an iterative process. It's iterative aspect without an endpoint. It goes on and on and on. And we can characterize this formally in the models that we have in cognitive linguistics. So in this, you have, let's say, the target domain of, we're going to set up a metaphor. This target domain is potential infinity. What we have is a process that begins and it goes on and on and on. Now, the source domain of the metaphor will be something very familiar. Namely, an iterative process that starts, that iterates a certain number of times, and then reaches an end state. It stops after some finite number of times. Now what we're going to do is understand the imperfective case, potential infinity, where things go on and on and on, in terms of an iterative case that stops after a finite amount. And the metaphor goes like this. We map the beginning state to the beginning state, the iteration to the iteration, and then we impose the end state structure onto the target domain where there is no end state. We add an entity via metaphor. Now, when you do this, this is a normal kind of metaphor to happen, there's an entailment. And the entailment from the source domain is that the end state is after all the other states, and it's the first thing after all the other states. Okay? So that's part of this metaphor. What we claim is that the end state that you put up top is actual infinity in all the cases. And then there are special cases. So if, for example, your iterative process is taking a number and making a larger set to all the previous numbers you have. You start with 1, you add the number 2 to get a bigger set. You start with 1 and 2, you add 3, and so on. You're iterating. And then you add an endpoint. Right? What that says is that that endpoint contains all the previous sets. And it's the smallest set containing them. Okay? Now, what about that point at infinity? Right? What does it mean to have a point at infinity? Here's a way to think about it. Imagine a triangle. Here's a little triangle. Looks like this. It has two angles, one here and one here. And it has, let's assume these lines are of equal length here and equal, okay. Now, what we're going to do is make these lines twice as long in each stage. Okay? We're going to keep just double the length. It could be any other number. Okay? So we're going to make it longer, longer, longer. So the iterative process is you start out with a triangle, and at each point you have another triangle with the sides twice as long. As they get longer and longer, the lines get longer, and the angles get closer and closer to 90 degrees. Until, when you add the end state, you still have a triangle, but the lines are infinitely long, and these angles are 90 degrees. That is, these are parallel lines, and they meet at infinity. That's what it means for parallel lines to meet at infinity. And since I've chosen this arbitrarily, with any distance and any orientation, this will be true for every set of parallel lines in any orientation at any distance from each other. In this geometry, they will meet at infinity, and now you know what that means. And by this way, what we do in this book, Where Mathematics Comes From, is go through most of the cases of actual infinity in higher mathematics and show how they are special cases of this single metaphor. And let me give you one more crucial example from mathematics. It's the notion of a real number. And it turns out a real number is deeply metaphorical because all real numbers require an application of the basic metaphor for infinity. Think, for example, of an infinite decimal. Right? You have decimal places 3.14159 ... and it goes on forever, but it's a thing. It's a particular thing that is infinitely long. It's actual infinity. Okay? That is, every real number works that way. And there are many different ways of characterizing real numbers. Those of you who have taken courses on this will recognize things like one way to characterize a real number is to take an interval on the real line and then a smaller one inside that and a smaller one inside that. And you go on and on and on, taking the intersections. And finally, the intersections of all of these intervals at infinity are a single point. Well, how do you get from the length to the point? Right? It's via this metaphor of actual infinity. And what we do is show exactly how that works in the book. At infinity, the distance is 0 between the 2 points. Now, why am I bothering to say this? What I'm doing is pointing out that we have this very lengthy treatment of metaphor in mathematics, showing that all mathematics uses conceptual metaphor. That means that mathematics itself is not out there as part of the world. Mathematics is not out there as part of the world. Now, many people think it is. And let me give you a couple of examples. At Berkeley, about several years ago, right after it was announced that Andrew Wiles had proved Fermat's last theorem. Okay, you remember this great discovery. Andrew Wiles, mathematician at Princeton, proves Fermat's last theorem. There's a great celebration around the world in mathematical circles. One of the things I especially love about Berkeley is on that occasion there was a convocation in a large auditorium and over 1,000 people came to celebrate the proof of Fermat's last theorem. That is wonderful at a university. Now, I went to this convocation, and a great mathematician at Berkeley, who was a friend of Wiles, got up to announce this. And he stated Fermat's last theorem, and he said, a to the n plus b to the n is not equal to c to the n for any n greater than 2. Very simple. And he says, we now know that this theorem is true, not only in Berkeley and in Princeton, but also in England. And not only in England and in America and in the Northern Hemisphere, but also in the Southern Hemisphere. And not only on Earth, but also on Mars. And not only on Mars and Earth, but throughout the whole solar system. And not only in this solar system, but also in Alpha Centauri. And not only there, but in every solar system in the whole universe. And not only in this universe, but in every possible universe. Okay? This is what I call the romance of mathematics. It assumes that mathematics is out there in the world, that it has an objective existence independent of the human mind. But if mathematics is fundamentally metaphorical, it cannot have an existence independent of the human mind. So that it's very important to know whether mathematics is metaphorical or not, because it changes utterly your understanding of mathematics. Now, one of the ways that we argue the case that mathematics isn't just out there is first by showing that actual infinity is metaphorical, but also by looking at other kinds of examples. For example, take the notion of a set in set theory. Now, most set theories are understood metaphorically in terms of a container metaphor. A set is seen as a container, a bounded region in space, where things are either inside the bounded region or outside of it. And one consequence of that view of a set is that a set can be a member of itself, because a circle, a bounded region, cannot be inside itself. Okay? So it's hard to even think of a set being a member of itself. However, a little over 20 years ago, certain mathematicians who were working on the semantics of computer languages decided they needed to have sets that were members of themselves. Why? Well, in the theory of formal languages, the way that you make sense and interpret a formal language is by mapping it onto some set theoretical structure. And in computer science, you have formal languages, formal statements, which are recursive, which apply to themselves. So you can do loops in computer science. And if you're going to interpret that in terms of set theory, that had to map onto sets that were members of themselves. Now, luckily, the people working at this, there's a wonderful article on this by John Barwise and Larry Moss in the Mathematical Intelligencer some years back. The people working on this read a book called Metaphors We Live By. And that book pointed out that we think metaphorically. And they realized that the container metaphor for sets was getting in the way of their doing mathematics of this sort. And they said, what we really need is to change metaphors. We need a notion of a set that isn't a container. And what they did was they came up with a different metaphor for sets. It's the metaphor for a set as a graph, you know, where you have a point that starts and an arrow to the next point, an arrow to the next point, where the arrow indicated set membership and the points indicated sets. And then if the arrow came back on itself, then we said the set was a member of itself. Okay? And when they did that, they got a new set theory, and then they were able to formalize the set theory with a set of axioms, and then they made it into a new branch of mathematics called a non-standard set theory. Now, which set theory is really there? The standard one based on containers, or the new one based on graphs? The answer is both are part of mathematics. Both are set theories. That is, if you don't have any loops, you get a reduction to ordinary set theory. Both are set theories. They're just based on different metaphors. That is, it is not the case that there is one subject matter set theory with one kind of set. The universe is not structured by unique mathematical entities like sets. And in fact, as anybody who studies set theory knows, what mathematicians who do that do is make up new set theories all the time, by the hundreds. There are lots of set theories, hundreds of them, just as there are thousands of kinds of logics, mathematical logics, each made up by mathematicians who like to study them. That is, they are not structuring the universe as entities, as unique entities. They are products of the human mind. That's important because science is done using mathematics made up by human beings. All of science is metaphorical, and mathematics is metaphorical. Metaphor and metaphorical thought is central to scientific thought, and if you're at the MIT of China, you should know this. Okay? And this is also true of the mathematics used in formulating linguistics. That is, when you make up a formal theory, whether it's a neural theory or a generative theory, you are using metaphor. And you're using metaphors in the mathematics itself. And then you're using another metaphor to apply the mathematics to a given theory. For example, as I mentioned way back in Lecture 1, which now seems 5 years ago, but was only last week, Chomsky has a central metaphor. It's the first two sentences of syntactic structures. It says that a sentence is a string of symbols, uninterpretable, meaningless symbols, that a language is a set of these strings, and a grammar is a procedure for generating that set. Right? That definition says that a natural language is characterizable metaphorically by the theory of formal languages, that a natural language is, quote, a formal language in the technical sense of recursive function theory. It says you can understand natural language correctly using the mathematics of recursive function theory, and that's a metaphor. Okay? What I argued in the first lecture was that that metaphor did not work, that it was false, and we can go back to some of those arguments in a while. But what I wanted to do was point out that the very statement of it used a theory of metaphor, and that there's no way to get around it. This is a very profound thing. Anyone who's doing any kind of science should pay attention to the metaphors that they're using in the science. Now, and that's why I started out with the fact that we have studied our own metaphors for metaphor. There's a reason for doing that. We're being responsible. Okay. What I've been doing in these lectures are two things. In the first 6 lectures, I outlined what the basic mechanisms of thought are as discovered in cognitive linguistics. Let me go over them again. There are frames, conceptual frames, which have a structure of various semantic roles, relations between the roles in various phases. That is basically what a frame is, sometimes called a schema.
There are image schemas which are made up of primary image schemas, which are things like container schemas, source path goal schemas, contact schemas, and so on. And these schemas have been modeled in the theory of neural computation by Terry Regier, who argues that they're computed by brain structures, that there are special brain structures in the brain that have been discovered that can compute each of these schemas, each of these primary schemas, and then we get complicated image schemas as we do in spatial relations like through or into, by putting these primary schemas together. Through has, for example, a container schema and a source path goal where you start outside, go inside, then go outside again. Okay? Where you combine those those primary ones together, you get complex ones. And the mechanism, he says, at the neural level is neural binding, and that each of these schemas is embodied. Right? The central idea in cognitive linguistics is embodiment. And if you take away nothing else from these lectures, it is important to know that all of our thought comes out of our bodies and brains and the way we interact with them in the world. That thought is not an abstract thing. Thought is not floating in air. It's not just, somehow abstract. Thought is computed by your neural system. And what we did in lecture 5 was show how. That is, we went through exactly studies taken from the work in mirror neurons at Parma, and showed how you could get at least one concept, maybe a couple more, but how concepts could arise and how abstract concepts can arise by actual neural computation. That is, all concepts are embodied in two different senses. One, neurally, they're computed by neurons, and two, because neural systems like the canonical neural system and the mirror system connect us to the world. Mirror neurons, remember, fire when either we are performing an action or we see someone else performing the same one. They link us to other people. Canonical neurons fire when either we perform an action or we see something we could perform it on. I drink, or I can look at the bottle that I could pick up and take a drink from. Okay? Same neurons would be firing. That neural system connects us to the things we act on in the world, connects us to the world. Okay? That is to say that meaning and concepts are based on neural systems is not to say that they are entirely internal. It is not to say that they are disconnected from the world. It is to say that they are connected to the world and to other people. Meaning is in our connections to each other and the world. And it's also embodied in the neural system and embodied in the way our bodies, as whole bodies, function in the world. So, for example, the embodiment of primary metaphor, take something like, he's a warm person as a metaphor. The metaphor of affection is warmth has to do with the emotional system that registers affection being activated, say when a child is held by his mother, and the metaphor that the notion of warmth, which is temperature. So when you're held, you're both experiencing affection and physical warmth. Two parts of your brain are activated, one at the temperature center, another at the emotional center, and they're regularly activated over and over so that metaphorical circuits are formed between them. What's going on in the physical system? They're not different. They're two sides of the same thing. They're not different forms of embodiment. They're two sides of the same form of embodiment. And notice what we're not saying. We're not saying that meaning is arbitrary. We're not saying that meaning is internal at all.
We're saying it's in the connections, and it's not arbitrary. Meaning is there in a certain shape because we have the kinds of brains and bodies we have. Image schemas are not arbitrary. They're there because we have brains that have topographic maps of the visual field and orientational cells that can compute orientations like up and down and front and back. If we didn't have cells in our brain and circuits that could compute up, down, front, back, and so on, we couldn't have concepts like that. Every thought you think has to be embodied through the neural system and also through your gross bodily functioning in the world at once. Two aspects of the same thing. Now, I mention this because the theory of cognitive linguistics is often misunderstood. One misunderstanding is it's claimed that we are saying concepts are just imagination. They could be anything at all. We're not saying that. We're saying that, in fact, there are universals, conceptual universals, metaphorical universals, universals that arise because bodies cannot be just anything at all. We all have brains of basically the same kind. We all have bodies of basically the same kind. Differences, to be sure, but we all have, eyes and ears and nose and arms, and we stand erect, and we have legs and toes, and we move, and the Earth is different. I mean, it's different to be in Beijing than it is to be in California, but not that different. I mean, you breathe air in both places, you drink water in both cases, there's gravity in both cases, and there's trees and grass and all those things. If you start listing the things that are the same, there are thousands of them. Okay? Those common experiences, given common bodies, give rise to common concepts that are not metaphorical and common metaphors as well. Those are the universals. Then there are things that have to do with culture, with taking primary metaphors and basic concepts and putting them together in new ways in different cultures. So are we claiming that meaning is universal? Partly. Are we claiming that meaning is not universal? Partly. Yes. We are not either universalists or relativists. We're in between. And we ask empirically which is which. It's an empirical question all the time. Okay? So it's important to understand that cognitive linguistics provides a very different understanding of what meaning is, what language is, because language expresses meaning. We'll talk about that in a while. And a different understanding of what mathematics is and what science is. Right? And all of a sudden you have something that grows out of linguistics and cognitive science and provides a new understanding of science itself, of mathematics itself, and of philosophy itself. In the lecture the other day on philosophy, what I did was this. I pointed out that Mark Johnson, who's the philosopher I've worked with most, a very, very close friend, an expert on the history of philosophy, had observed that virtually no Western philosophies were consistent with the data on cognitive linguistics. That is, and the reason was they're virtually all disembodied, with a few exceptions like John Dewey and Merleau-Ponty, but Dewey and Merleau-Ponty did not have notions like metaphor and image schemas and anything as rich as that. They just noticed that language was embodied, that thought was embodied, somehow. So what we've done is given a method for showing the details. What are the mechanisms of thought? Now, in doing that, we've discovered that virtually all philosophies in the West are disembodied philosophies. And they're disembodied for certain interesting reasons. One of them is that they begin with the question, how can we get true knowledge of the world? And they assume that we get our concepts from the external world, not from what our bodies are like. and that therefore our bodies are independent of what the world is. They assume that there's an objective understanding of the world and that our concepts come from the world as structured independently and objectively. This has been true from the Greeks all the way up through present Anglo-American philosophy. It's a common understanding that runs through Western philosophy, and it requires disembodiment, and it's assumed that the body gets in the way of knowledge. That bodies are imperfect. They can fail. They can screw you up. Your vision can be wrong. You can have hallucinations. Therefore, the bodies get in the way of truth. Truth is out there in the world. You can sometimes get it, but your bodies get in the way of it. The reverse is true. It's your bodies and your brains that make truth possible. And the reason they make truth possible is that they make understanding possible, and truth is based on understanding. Think of it this way. If I give you a sentence and you don't understand what it means, how could you tell if it was true? In order to tell if a sentence is true, you at least have to understand it. If I put a bunch of random words together and I say, run, bottle, microphone, the, I give you some random words and you don't understand them, and I say, is that true? You can't have the words fitting the world. I mean, no way. Right? And in general, metaphorical sentences can be true. As we said in a couple of lectures ago, sentences like, he wasted an hour of time this morning, which is like, assumes a time is money metaphor. Or I invested a lot of time getting a linguistics PhD, and now it's worthless. Now, that metaphor of investment of time is a metaphor. Time is not external to people, something that can or cannot be invested. It's a metaphor. It's part of your mind. Yet, if you understand the world in terms of that investment metaphor, that sentence could be true. Or someone, in fact, could waste an hour of your time this morning if you understand time as a money-like resource. Right? If you don't have that metaphor at all, then it's meaningless. And not everybody in the world does have that metaphor. Now, that's a very profound thing. It says that truth is not independent of people. Truth depends upon how you understand something, and you understand things in terms of what? The mechanisms of thought, frames, image schemas, metaphors, metonymies, blends. Those are the mechanisms that you understand in terms of using your neural system. Okay? So those are important things to know, and they lead to a new philosophy. They lead to a philosophy that says that understanding is central. That understanding occurs via neural computation, that is what we call simulation semantics, that you're neurally simulating the world. And the reason you can do this is another discovery from neuroscience, that the same neurons are firing when you either act in the world or perceive or imagine acting or imagine perceiving. The same neurons are firing, and that therefore imagination is central to understanding. If you can't even imagine what it is to take a drink out of a bottle, you can't understand the sentence, he took a drink out of a bottle. I mean, you have to at least be able to imagine it. Now, that imagination is embodied and linked to the world, as we've seen. So that is a very different philosophy, basis for a philosophy. And then when you go to apply it to
concepts like causation and time, which we saw the other day, and the self and the mind and morality, we discover certain amazing things. It had been assumed in previous Western philosophy that there was only one causation in the world. There was only one correct logic of causation. We've discovered that there are over 20 different ones. That every different verb of forced motion gives you a different logic of causation. Verbs like bring and carry and throw and so on. They all can be used in causal sentences, but with different logics. And if we go through our book, we have about 24 different logics of causation, depending upon which metaphors you're using with which verbs of force, because there's lots of different kinds of force and logics of force. Once you notice that, you notice that there isn't one thing. If you say, what caused that? The answer first must be a question. What kind of cause are you talking about? There are different kinds of causation. And it's important if you're studying science. Science studies causation. Which kind are you looking at? Are you looking at causation as correlation? Are you looking at causation as force? And if it's force, is it force over time, continued application of force, initial application of force, etc.? So if you take a look at chapter 11 of Philosophy in the Flesh, you find a nice list, lots and lots of types of causation. And when you're studying science, you can ask yourself, which is it? Let me give you another example. Suppose you're studying economics or political science. In economics and political science, as done technically, probably here at Tsinghua University, since this is a technical university, the models used are called the rational actor model. That's one of the major models used. And in the book Philosophy in the Flesh, we have a chapter studying the cognitive structure of the rational actor model. The rational actor model assumes that every person is rational. And what does rational mean? It means pursuing self-interest in an optimal way, as well as possible. The assumption is that every person pursues their self-interest all the time, and they do it as well as they can, as well as can be done. And then they make up mathematical models of this form of rationality. The idea behind this is that if you're not pursuing your self-interest, you're just irrational. Okay? Now, we'll come back to that in a moment. The mathematics of this system is something that I analyzed with, it uses game theory, and a form of game theory. And I sat down with the Berkeley game theorist who teaches this, and we asked, what is the metaphorical structure of this mathematics? And we figured it out. It turns out to have a metaphorical structure. We also asked, what is the pure math behind this model? In game theory, whenever they introduce it, they talk about it in terms of winning strategies or losing strategies or rational action. But winning and losing and rational action are not parts of abstract mathematics. So we asked, what is the abstract mathematics? It turns out to be a bit of formal language theory plus probability theory of a certain kind, and we sat down and wrote it down. Then looking at the mathematics itself, it turned out that the mathematics had nothing to do with rational action at all. It was just mathematics. You could prove theorems in abstract symbols, and they said nothing about action or rationality in themselves. So we asked the question, what is the difference? How do you go from the math, the abstract math, to the idea of rational action? The answer is 3 layers of metaphor. You have to have a layer of metaphor to go from one kind of math to a way of understanding math in terms of branching trees, and then you have to have the event structure metaphor, and then you have to have other metaphors like Um, a firm is a person, or a country is a person, and so on. Now, why should anyone care whether or not the theory of rational action is metaphorical? Why should anyone care about these metaphors? Well, when you look at them in detail, there's every reason to care about them. In detail, these metaphors, like all other metaphors, have entailments. That is, in order to have a theory of rational action with this metaphor, there must be a starting point. Time must have a beginning. And in order to know which course of action has the most value, the highest utility, you have to have an ending point at which you compare utilities. Time must have an end. It has an ending point. Now, real time doesn't have a beginning and ending point, at least in normal human affairs. But in these cases, you must do it. That is, in order to apply this, you have to apply it over a certain amount of time. Now, you might say, where are these models applied? Well, one of the most important places they're applied is in war. These models were developed in the United States by the U.S. Air Force for war. And one of the places that they've applied them is in the Gulf War and the Iraq War. And so in these models, in the Iraq, for example, in the Gulf War, there was a discussion before the war of these models. And the question they asked was, is it worth it to go to war? Worth it. That is, it's like money. You know, you're understanding these models in terms of how much advantage, how much money almost you could get, but you're understanding it in terms of just numbers. Okay? Is it worth it? Okay? In terms of what's called utility. And then, in order to answer that, you have to be able to map this model onto Iraq and the American Army, okay? And the Iraqi Army. Well, in the, let's say, the first Gulf War, the way this was used, the mapping went like this, that in order to have a loss, you had either a gain or a loss for something to be worth it. You had to have the more gains than losses. Right? What's a loss or a cost? What's negative? Well, if one of your soldiers gets killed, that's a cost, okay, to you. If one of their soldiers gets killed, that's a gain. It's a funny way to think about things. Unfortunately, not funny, sad way to think about things. But that's how it is. So killing their soldiers is a gain, having your soldiers killed is a loss. Having your material blown up. They blow up a tank, you lose. You blow up their tanks, you win. Okay, that's a gain. What about people? Ordinary civilians. They don't enter into the calculation. They are off on the side. They're not in the calculation, except as propaganda. That is, if you wind up bombing a hospital, then there's a propaganda loss. So that is in the calculation. But otherwise, the loss of civilian lives doesn't count in the rational actor model. Okay? What about the ecology of the Gulf? Saddam Hussein let all that oil into the Gulf. Okay? Colin Powell in the first Gulf War was asked, when Saddam Hussein threatened that, he was asked, would there be any cost to Saddam Hussein doing this? And he said, no, our troops could still land. That is, from the perspective of the model, the ecology of the Gulf, which was destroyed, all those fish, shrimp, etc., sea life destroyed, didn't come into the calculation. It doesn't count. Okay. Now, what's interesting is that you have to say, metaphorically, what is a cost and what is a gain in order to apply this model. And when you do that in a war, you're doing something inhuman. Moreover, look at the present Iraq War. It had a beginning when they started the war. It had an end point
When they declared the war over, Bush came on the aircraft carrier, had a helicopter land, he came out in the flight suit and said, "We won, all over," right? And the model ended, and we won. But history didn't end. It's still going on and on and on, even though the model said that was where it ended. Right?
It matters that the rational actor model is used in calculations about war and foreign policy, and it matters what the metaphors are that apply it, and that it is a metaphorical model. It matters a lot. Cognitive linguistics teaches you this, and cognitive linguistics matters. Now, why should anyone from China want to do cognitive linguistics? Like you, for example. Why should anyone from China want to study this field? Well, first, the Chinese conceptual system is not the same as the American conceptual system. The point is that metaphor shows up everywhere, in politics, in everyday life, in science, in mathematics. And if you're going to understand your life, your society, your culture, your politics, you need to study it. And only you can. People from America may be able to help a little bit, but you have to study your culture, your language, your minds. Right? I can help you by giving you some tools, but you have to do it. And in the process, you'll probably learn that the theory doesn't work in some places, that it has to be fixed up, that new theories have to be developed. Right? That's something that you might only find out by studying Chinese conceptual systems, but not English ones. The counterexamples may be in Chinese, but not in English. Right? The more people study different conceptual systems around the world, the more people get respect for the human mind and for the differences among human minds, as well as for the similarities. It is important, if we're all to live together in one world, to understand how we are similar and how we are different, and to have an understanding, at least, of those differences, and preferably a respect, and preferably to be able to understand it well enough to work out means of accommodation. To do that, cognitive linguistics is an important tool. So it's extremely important for people to study Chinese cognitive linguistics. And not just important for you, important for me. Because as an American, I will be affected by the way Chinese understand the world. Just as you are affected by the way Americans understand the world. Let me go through some more kinds of cases, and maybe go back to some more linguistics. One of the things I mentioned in Lecture 5 is that by understanding the neural theory of mind and language, we get a better understanding of language acquisition. Why is it important to study how language is acquired, first language is acquired by children? Why does that matter? Okay. Now, we have recently learned through the work of Michael Tomasello and his colleagues in the Max Planck Institute in Leipzig that children, when they first learn grammar for individual verbs in particular settings, and the individual verbs describe particular actions like giving things, falling, hitting people, pulling things, pushing things, putting things in things, and so on. Okay? And they start there. They start with the way they act on the world, and then they extend, generalize. And I observed that the theory of cogs, which I mentioned in the Lecture 5, could account for generalizations. That the generalizations are actually in the special cases. and that you do not need a theory of induction to do this. What this says is that by studying language acquisition, you can find out something about the nature of induction. But there's more. Language acquisition determines how language is going to be in adulthood. That is, when we find out, let's say, how children learn metaphor, and they learn metaphor by having two domains of experience come together, right? That understanding has led us to understand that metaphor is there neurally, that it's part of neural computation for ordinary people, that everybody learns it unconsciously and automatically, and it gives us an appreciation for how much you can know without knowing that you know it. Little children don't know that they think metaphorically. Most adults don't know that they think metaphorically. But by studying language acquisition, we can find out about things like the development of metaphor, and we have. A crucial piece of the information came from language acquisition studies. A crucial piece of our understanding of grammar and generalizations in grammar is coming from the work of Tomasello. And we find through that work that grammar is embodied. How? When grammar is learned, verb by verb, action by action, experience by experience, like giving, taking, hitting, pulling, pushing, falling, and so on. When it's learned case by case in terms of classes of basic childhood experiences, right? That means that grammar is embodied in those experiences, that those basic childhood experiences will limit the possibilities for basic constructions, and that the basic constructions will be limited around the world because children pretty much function the same way. That is, a lot of the universality of grammar is going to come out of the universality of childhood experience. That is one of the morals we learn from Tomasello. It's a deeply important moral. And it's important in the theory of grammar itself because we now have a theory of grammar, Chomsky's, in which there's no experience whatever in grammar. Grammar is supposed to be there when you're born. Experience is supposed to be irrelevant. We know from Tomasello it isn't, but it's supposed to be irrelevant. And meaningless. That is, grammar is supposed to be just the learning of formal systems without regard to their meaning. Utterly ludicrous. Now, it's important to know this because when you really are understanding grammar, you need to know why you have the patterns you have. You're going to be hearing a visiting lecturer in a couple of weeks. In fact, I think it's a week. A week from today. Adele Goldberg will be here. Adele Goldberg did a marvelous dissertation at Berkeley. She was one of our students. And a great book called Constructions. And one of the results in that book was this. She took the double object construction of English, like I gave him a book. And she said, what is the relationship between that and something like I told him a story? And she pointed out that the relationship was metaphorical. That it wasn't just in the grammar itself, that it arose from the metaphorical system. And then she took 20 other kinds of double object constructions, and she showed that those too were metaphorical, and that metaphor was central to the generalization in grammar. Now, that is not something you could find out in a Chomskyan theory, because it's not, you can't look at metaphor there. You would never notice it. The original empirical work was done by two generative grammarians, Georgia Green and Dick Early, who were both Chomskyans. And they just piled up lots and lots of data and never figured out the generalization. It took Adele Goldberg to figure out that metaphor stood behind the generalization. Okay? Very important thing to know about grammar itself if you're studying grammar. Now, there may be other things like that that we could talk about. But what I wanted to do was this. I wanted to summarize by giving you some notion of the importance of what we're doing. And then I wanted to finish by talking about what we might look forward to. What would this be like 10 years from now? 10 years from now, I can be sure that we will know a lot more about neuroscience. A huge amount more. And it turns out that every bit that we learn, year by year, increases our understanding of how we think and our understanding of language. It's been absolutely remarkable. I would never have guessed when I entered linguistics 42 years ago, 42 years ago, I'd never even imagined saying such a sentence, that I would be working with people who understood enough about the brain to explain how we get concepts and how our concepts are connected to the world. I would never, ever have guessed that that was possible. We cannot guess what neuroscience will tell us next, but we do know that there's going to be a lot more, and it's important to know it. The reason I started with that is that most linguists don't bother reading neuroscience, and they should. If linguistics is cognitive linguistics, then neuroscience is a normal thing to read because it's part of cognitive science. If linguistics is seen as an autonomous discipline, separate from everything else, you'll never learn what neuroscience has to teach you. You'll never find out. And you'll never learn what cognitive psychology or developmental psychology will have to teach you. You'll never learn what other sciences have to teach you, what anthropology has to teach you. Language is affected by everything, and language affects everything. It lies at the center of all subject matter in the university. Language, or I take language in the sense of studying ideas as well as linguistic forms, metaphors, frames, and so on, applies to every form of knowledge. We've seen how it applies to economics, how it applies to political science, how it applies to poetry and poetics. We've seen how it applies to politics, to philosophy, to mathematics, to science. It applies everywhere. And to understand it, you have to understand many other disciplines. A university is a place where all disciplines come together. That's why it's called a university, as in universe. It's the universe of disciplines. Linguistics is the right discipline. Cognitive linguistics is the right discipline to be in a university. Cognitive science is a central discipline to any university. And I understand that there's plans to set up a cognitive science program here. And I hope that those who set it up will remember that. That you can't just say, well, it's actually four things: neuroscience, psychology, linguistics, some philosophy, linguistics, computer science. It's not. It is linked to everything. And the reason is that the mind and language are linked to everything. If you become a linguist, you have the tools to study all kinds of interesting things. You can have a lot of fun. I have a lot of fun. Honest. I get to study, think of all the fun things I get to study. I get to study poetry. I get tired of poetry, I can study mathematics. Get tired of that, I can study politics. Then I can go back to studying grammar. I can, think of all the fun things I can do. And you can do. Okay? So, that is why I thought it was important to talk about all of the things I've talked about. All the modes of thought that we've learned about, what we've learned, where we've learned it from, and what we can apply it to. Thank you.